Okay, let's unpack this. Imagine, for a moment, the world of AI models. They're brilliant, right? But they have this massive Achilles heel, remembering context, especially over really long conversations and generating complex thoughts without tripping over themselves. For years, researchers have stared at these behemoths thinking there has to be a better way for them to manage memory and generate faster, particularly for multi-step reasoning.
Yeah.
And then you have this aha moment, that flash of insight where you see the path forward. So you decide to build something fundamentally new. You engineer this revolutionary decoder-hybrid-decoder architecture, and you call it SambaY. You tuck these ingenious gated memory units inside, making them share what are called state space model states, or SSM states, across layers, and suddenly the impossible becomes real. No more positional encoding needed, pre-filling is still linear, and decoding just gets, well, faster. You train it up, putting it head-to-head against YOCO, that tough baseline known for its efficiency, and SambaY's irreducible loss. That's a measure of its ultimate performance potential. It dips significantly lower. This means it scales better when compute swells. You put it through its paces on long context benchmarks like phone book and ruler, and get this, even with a tiny sliding window of just 256 tokens, it outperforms. No sweat. So you build out a large-scale prototype, 5-4 mini flash reasoning, adding in a clever component called differential attention, and you train it on 5 trillion tokens. Critically, you achieve this without incorporating a single reinforcement learning stage. You pit it against the strong 5-4 mini reasoning baseline on challenging benchmarks like Math 500, AMBE 2455, and GPQA Diamond, and it crushes them, all while decoding 10 times faster on 32,000 token generations. They say, but it's just a hybrid model, not a pure transformer. You show them the throughput, 10x speed on long chain of thought sequences. They say, but state space models lack expressiveness for complex tasks. You point to the scaling curves, the lower loss, the unprecedented reasoning abilities. You open source the code, put it out there for everyone, and they realize you didn't just tweak a model, you completely rethought how memory flows between layers, between decoders. You built a bridge between efficiency and raw power. For every long sequence, every chain of thought that will ever need sophisticated AI reasoning.
That's quite the narrative of innovation, isn't it? The core challenge in this field often boils down to balancing raw computational power with, well, practical efficiency, especially when dealing with the ever-growing demands of understanding and generating long pieces of text. What's truly fascinating here is that the source material we're diving into today chronicles exactly this journey, revealing how a novel architectural approach like SambaY significantly addresses these critical bottlenecks in large language models.
Absolutely. Our mission today is to take a deep dive into this groundbreaking paper, Decoder-Hybrid-Decoder Architecture for Efficient Reasoning with Long Generation by Ren et al. We'll explore how they rethought memory flow, what these ingenious gated memory units actually do, and how they manage to achieve truly staggering performance and speed gains, especially for those complex multi-step reasoning tasks that really push current AI models to their limits. So let's start at the beginning. What problem was SambaY designed to solve? Traditional transformer models, while incredibly powerful and dominant in language modeling, have a well-known limitation. Their core attention mechanism has a quadratic complexity for long sequences. What does that mean in practice?
It means that as the length of the input text or the text being generated increases, the computational cost doesn't just go up a little, it explodes. It's like trying to juggle more and more balls, but each new ball adds exponentially to the effort. While earlier innovations, such as YOCO, a model designed to improve efficiency, managed to achieve linear pre-filling, meaning it could process long initial prompts efficiently by reusing key value or KV pairs. It still struggled.
Right.
YOCO hit a wall with high memory input-output costs during the generation or decoding stage, particularly for long chain of thought or COFI reasoning.
And that's where models generate those extensive multi-step explanations.
Exactly. And that's precisely where efficiency really matters in real-world applications. You need that speed during generation.
And that's where the gated memory unit, or GMU, steps in as a truly central innovation. This isn't just a minor tweak. It's the core contribution of this paper. A simple yet effective mechanism for efficient memory sharing across layers. It's designed to be incredibly versatile and, well, smart about how it handles information.
Precisely. Think of the GMU as a very smart filter, kind of. It takes the current layer's input and combines it with a memory state from a previous layer specifically. In SambaY's design, these are states from state space models, or SSMs. The real magic lies in its gating mechanism, which uses clever mathematical operations, element-wise multiplications and learnable projections to dynamically recalibrate how information from previous layers is mixed with the new input.
Okay, so it's dynamically choosing what's important from the past memory.
In essence, yes. This allows the model to intelligently filter and combine information, ensuring only the most relevant memories influence what it generates next, all without the heavy computational burden of traditional attention.
And the why it's efficient part is crucial, right? How does it save computation?
By replacing approximately half of the computationally expensive cross-attention layers with these far cheaper, element-wise gating mechanisms, GMUs significantly reduce the number of parameters and overall computation needed. What's more, the GMU is remarkably adaptable. It can gate other memory sources, like those from attention or multilayer perceptron or MLP layers, though the research highlights that its effectiveness in retrieval highly depends on the specific characteristics of that memory source. It's not a magic bullet for any memory type.
Right, so the choice of SSM memory was key.
Very much so. And that brings us directly to the SambaY architecture itself. It's cleverly designed as a decoder-hybrid-decoder model. You can visualize it as a specialized two-part system. It uses Samba as its primary self-decoder, which is itself a hybrid, interleaving a state space model called Mamba with a technique called sliding window attention, or SWA.
Okay, so Mamba and SWA working together in the first part.
Exactly. The GMUs then come into play in its cross-decoder, acting as the intelligent bridge that allows for highly efficient memory sharing between these different powerful components.
And the efficiency gains this design unlocks are genuinely striking. You mentioned decoding earlier.
Yes. For decoding, which is the process where the model generates its response, SambaY drastically reduces memory input-output complexity for its GMU layers. Instead of computational cost scaling linearly with the length of the output sequence, which, as we discussed, is a massive bottleneck for long generations, it scales constantly with the hidden dimension of the model.
Which is huge, because N, the sequence length, is often much bigger than the hidden dimension, right?
Awesomely. This is critical for long outputs where the generated text can be much, much longer than the model's internal processing dimensions.
And it keeps the linear pre-filling time, too.
It does. It maintains the linear pre-filling time complexity from earlier models, so initial prompts are processed quickly. And it even simplifies the model by eliminating the need for explicit positional encoding, like ROPE, a technique commonly used in transformers.
So faster generation, fast pre-fill, simpler design. It sounds almost too good. Are there trade-offs?
That's a significant leap forward, certainly. However, it's important to acknowledge a current limitation. Even with these advancements, SambaY still includes at least one full attention layer in its design.
Okay.
This means that the per-token computation complexity during decoding remains linear. While far better than quadratic, it does point to a clear area for future research, perhaps integrating dynamic, sparse attention mechanisms to push efficiency even further for truly extremely long sequence generation.
Right. Always room for improvement. Now let's talk about the results, because that's where SambaY's true power shines. The researchers employed a very rigorous method called Oinki++Ide, pronounced P++, I believe, to compare the scaling capabilities across different architectures. This isn't just about making models bigger. It's about seeing how well they truly improve as they scale. And SambaY shows superior scalability with this method.
Indeed. A critical metric they measured is irreducible loss, often denoted as C. This is essentially the theoretical best performance an architecture can achieve with, infinite training data and compute. It's the floor, theoretically.
Okay.
SambaY exhibits a significantly lower irreducible loss of 0.58 compared to other leading architectures like Rusio at 0.61 and Transformer++ at 0.64.
Lower is better here.
Lower is definitely better. It tells us SambaY has a superior long-term performance potential, meaning it can fundamentally reach better results with more resources. The P++ scheme itself is vital because it's a principled method that ensures a truly fair apples-to-apples comparison of how well different architectures scale. It proved more favorable than standard parameterization methods and showed that under proportional scaling of model size and data, these hybrid architectures like SambaY demonstrate superior scalability, especially in what are often data-limited training scenarios compared to pure transformer models.
So it's not just about theoretical scaling, it's about practical performance, especially in tasks known as efficient long context retrieval. This is where AI models have to pull out specific information from very long pieces of text.
Right, finding the needle in the haystack.
Exactly. SambaY achieves superior performance on challenging long context tasks, like phonebook, which is a realistic multi-key value retrieval task, and also ruler. And it does this even with that modest sliding window attention, or SWA, size of just 256 tokens.
What's quite surprising from their SWA findings, actually, is that larger SWA sizes didn't consistently provide better results.
Really? You'd think bigger would be better.
You would, but in fact, smaller SWA sizes, like that 256, actually allowed SambaY to focus better on local patterns and mitigate attention sinks areas where attention mechanisms can get stuck or perform poorly. This led to faster convergence in data-limited scenarios.
Interesting. So sometimes less is more with attention windows.
It suggests a more nuanced understanding of how attention should be applied, yeah. Overall, it's clear that hybrid models incorporating state space models consistently outperform pure transformer architectures in these long context retrieval tasks.
And then we get to the ultimate test, the Phi-4 mini-flash reasoning triumph. This is a large-scale prototype model coming in at 3.8 billion parameters, built on the SambaY architecture combined with differential attention. The results are frankly remarkable. It significantly outperforms the strong Phi-4 mini-reasoning baseline on challenging reasoning benchmarks like Math 500, AME 2425, and GPQA Diamond. These are really tough tests.
What makes this particularly impressive is the no RL feat. It achieved these significant gains without incorporating a reinforcement learning stage, which the Phi-4 mini-reasoning baseline actually used.
So it's beating a model that had extra training optimization.
Precisely. Phi-4 mini-flash reasoning relies only on supervised fine-tuning, SFT, and direct preference optimization, DPO. This highlights the sheer strength of the architectural design itself, rather than relying solely on complex post-training optimization techniques.
And for real-world applications, this is where it gets really impactful. Phi-4 mini-flash reasoning delivers up to an incredible 10x higher decoding throughput when processing 2,000 token prompts and generating responses up to 32,000 tokens long, especially for complex chain-of-thought sequences.
10 times faster, that's huge.
It's massive. We're also talking about a 4.9x speedup in long context processing overall. Think about that for a second. If you're building an AI assistant that needs to generate lengthy explanations or engage in complex multi-step reasoning.
Yeah, that's the difference between waiting minutes for a response versus getting it almost instantly.
Exactly. That's a game changer for user experience. The model even exhibits advanced reasoning, such as double-checking, reflection, and backtracking in complex math and daily life reasoning. Like, they mentioned it self-correcting its letter count in a misspelled word like strawberry by guessing user intent.
That level of nuanced reasoning combined with the speed is truly impressive.
Okay, so let's move into the ablation studies. These experiments are like dissecting the model to understand why SambaY works so well, right? Isolating the impact of each design choice.
Exactly. First, looking at the choices for the self-decoder architectures, the research explored alternatives to Mamba. Replacing Mamba with Mamba 2 in SambaY actually led to a significant drop in accuracy on long context tasks.
Oh, interesting. Why was that?
Well, the paper suggests this is possibly due to Mamba 2's coarser forget gates, which might reduce the model's ability to retain fine-grained positional information needed for those long contexts.
And this really underscores the continued importance of the sliding window attention, doesn't it?
It does. The weaker performance of pure Mambo, that's the variant without SWA, compared to the full SambaY, clearly highlighted that the local retrieval provided by SWA is crucial. Simply relying on the recency bias from a state space model like Mamba isn't sufficient for complex retrieval tasks. You need both.
Makes sense. What about other architectures they looked at?
On a different note, they also found that gated DeltaNet, or GDN-based models, achieved impressive accuracy due to their enhanced retrieval capabilities with what they call delta update rules. And combining GDN with short-range SWA surprisingly accelerated training without much degradation. So more evidence for hybrid approaches.
Okay, and what about the GMU itself? Did the memory source matter much?
Yes, significantly. The ablation studies investigated how the GMU's memory source impacts performance. While GMUs are versatile and can work with memory from attention and MLT layers, their performance on retrieval tasks depends significantly on the memory source's inherent characteristics. For example, gating SSM memories, as in the original SambaY, performed better on the phone book benchmark than gating attention or MLP representations.
Why was that?
It seems because SSMs naturally provide a recency bias, which is highly beneficial for retrieving contiguous information, making them ideal partners for the GMU in that kind of task.
And this gets even more specific.
Yeah.
They tried removing all the cross-attention, right, in a variant they called SambaY.
They did, and it led to significant degradation in performance. This highlights that a sufficient number of cross-attention layers are still necessary for successful retrieval from large key value pools, even with the GMU's innovations streamlining the process.
So you can't just throw out all the attention.
Not entirely, no. It's a testament to the carefully balanced hybrid approach.
Right. And maybe one of the most surprising or subtle findings was about normalization.
Yes, perhaps one of the most critical findings from the ablation studies concerns the normalization placement within these linear attention layers, particularly the GMU. It was discovered that retaining the normalized GMU or NGMU, and specifically applying RMS norm after the output gating, is critical for long context retrieval performance.
So where you put the normalization really matters, even if it seems like a small detail.
A huge impact. Shifting that normalization before the gate severely degraded long context performance, even if it had minimal impact on short context tasks.
Wow.
This vividly demonstrates the profound importance of maintaining the correct processing order, the associativity between gating and token mixing. It's about ensuring the model processes information in the most effective sequence to maintain its long-range understanding. It's not just what operations you do, but the order.
Fascinating. Okay, so like any cutting-edge research, they also talked limitations and future work.
Absolutely. As with any cutting-edge research, this paper outlines important limitations and future directions. For instance, reinforcement learning, or RL, remains underexplored in the context of hybrid architectures. While SambaY achieved impressive results without RL, further integrating it could potentially unlock even greater performance down the line.
And I remember you mentioning hyperparameter tuning.
Yes. It's important to acknowledge that due to resource constraints, an exhaustive hyperparameter search wasn't performed for every single architecture variation tested.
Which is understandable.
Completely. But it means that with more aggressive tuning, there's a strong likelihood that these models could yield even further improvements. It's exciting to think about what more could potentially be squeezed out of this design with more compute time for tuning.
And the last limitation ties back to something you mentioned earlier, right? The linear decoding complexity.
Exactly. A key limitation highlighted again is that the architecture still includes a full attention layer. This means that per-token computation complexity during decoding remains linear. While significantly better than quadratic, as we've said, it's a clear path for future research on integrating dynamic sparse attention mechanisms to further improve efficiency on extremely long sequence generation, particularly for very long, complex agentic applications where you might generate millions of tokens.
Gotcha. So wrapping this up, what does this all mean for the future of AI? We've seen how SambaY, with its ingenious gated memory units and smart hybrid design, isn't just a minor improvement. It feels like a fundamental rethinking of how memory flows in these powerful language models.
I think that's fair to say.
It's built a highly effective bridge between efficiency and raw power, setting new benchmarks for long context understanding and generation. It truly is a testament to how rethinking core architectural components can lead to transformative gains.
Indeed. This deep dive has really highlighted that even with existing powerful components like SSMs and attention, innovative architectural designs and careful consideration of things like scaling laws can unlock unprecedented performance and efficiency. It really raises an important question, doesn't it? What kind of complex, multi-step reasoning problems become truly tractable and widely accessible when models can process and generate information with this level of speed and accuracy, even on, say, a modest hardware footprint?
It makes you wonder, doesn't it? If the bottleneck of memory and processing speed is being tackled so effectively, what new frontiers of AI reasoning and understanding will open up next? This research really lays out a compelling path forward for language models to tackle ever more complex tasks efficiently, something to mull over until our next deep dive.